Chemistry and Honors Chemistry. This is a new unit called equilibrium, and we're going to start off talking about something called the equilibrium constant. So what is equilibrium? Equilibrium is the final state of a chemical reaction in which the concentration of reactants and products remain unchanged. So some chemical reactions run until all of the reactant have turned into products. That's pretty much what we've always assumed in this class, that you start off with certain reactants that you put in the beaker or whatever the vessel is that you're working in, such as A and B here, and by the end of the reaction you start off with all of that and none of the product C. And by the end of the reaction, we call that the final state, you end up with all product over on the right and no reactant. So the reaction has gone completely from left to right. So reactions that move only from reactants to products are called irreversible reactions and have an arrow pointing from left to right, and that's what we've always seen. Most reactions can move both from reactants to products and from products to back to reactants. Again, most reactions can do this. These reactions are called reversible reactions and are shown by a double arrow. So in this case, you have a reversible reaction that takes the reactants A and B and turns them into C, but it also means that C can go back to A and B. So let's say that the final state of this, I'm just making up these numbers, is you started off with 100% reactants and no products. By the end, the reaction doesn't go all the way to products, all the way to C. It goes about 75% towards C, but there's still 25% of the reactants left in the container. That's generally what reactions do. So that's an example of a reversible reaction, and that 25-75 balance is called the equilibrium of the reaction. So here's one with initial state of 10% reactants and 90% products. So let's say that in the example right up above that the 25-75 is the natural balance that reaction wants to find, and it's at a particular temperature and particular concentrations. So let's say you start off with only 10% reactants A and B and you put 90% products into the same vessel. Then the final state will be the same, 25% AB, 75% C. So that situation where it's 25% reactant, 75% products is called its equilibrium. It's happy there, and the reaction will just stay with those concentrations of reactants and products. In the reaction above, it doesn't matter whether the reaction starts with 100% reactants and 0% products or with 10% reactants and 90% products. In both cases, the reaction will stop when there are 25% reactants and 75% products. This is the equilibrium for the reaction. A reaction at equilibrium is in a state of dynamic equilibrium. Dynamic equilibrium means that the reaction continues to move back and forth, but does so at equal rates. So let me give you an example of that. Let's say that in my classroom there's 12 students. I'm room A, and Mr. Andrews next door is room B, and he has 7 students. And let's just say that's where everybody's happy, to have 12 in my room and 7 in his room. Now let's say that 5 of my students move over to Mr. Andrews' room. So now I have 7 and he has 12. It could be any number that I'm picking here. So 5 move from room A to B and 5 move back from A to B, like that. So now I'm back to having 12 students and Mr. Andrews is back to having 7 students. 5 moved over to his room, 5 moved back. It may be a completely different 5, it doesn't matter. Now let's say that 2 students move from my room to Mr. Andrews and then 2 move from his room back to mine. Again, could be 2 different students, like that. So room A ends up with 12 again, what I started with, and B, 7 again, even though people moved back and forth. This is dynamic equilibrium. So it means at any time I'll have 12 students and Mr. Andrews will have 7, but it won't be the same 12 and the same 7. That's totally unimportant. It just means that when a reaction is in equilibrium, the point of this concept, when reaction is in equilibrium, it doesn't just stop. It's reactants turning into products, but then products turning back into reactants at equal rates. And if that happens, then in this case of this example, room A will always have 12 and room B will always have 7. Maybe for very small amounts of time, those will be different, but generally speaking, on average, it'll be 12 on the left, 7 on the right. The equation used to measure equilibrium is called the law of mass action, and I usually use that term, but sometimes it's just simpler to call it the equilibrium equation. So here's an example of a law of mass action for a hypothetical reaction. So the law of mass action for this reaction is, okay, let's look at this. So there's a lot going on here that you're being introduced to. Kc is the equilibrium constant. And if you look at what's on the top, it's the products. It's what's on the right side of that chemical equation, and that's C and D. Now they're in square brackets, so that means it's concentrations. We're dealing with solutions here, and those are concentrations of products. C and D are the products. And you'll notice the exponents are 1 and 4. Those are the coefficients in front of C and D. So the coefficients become the exponents in the law of mass action for this reaction. Down on the bottom, you see the reactants, A and B. And they're also in square brackets, meaning that those are concentrations. It's molarity. And that's why when we talked about measures of concentration, molarity is pretty much the only one we're going to talk about from now on. There might be a few brief exceptions, but generally not. So the concentrations of A and the concentration of B, and then again, you raise them to the power of their coefficients, 2 and 3 respectively. Okay? So that's the law of mass action. Don't get too lost in the details to understand what this is telling you. It's telling you that what's on top is the products, what's on bottom is the reactants. Okay? So let's see how those relate. Kc is called the equilibrium constant. The subscript C refers to the equilibrium of a concentration of a solution. So equilibrium constants have no units of measure, by the way. So the equation used to measure equilibrium is called the law of mass action. We will often simply call it the equilibrium equation. Same thing. So here's the example again. So the law of mass action for this reaction is, so the products are on the top and the reactants are on the bottom. So think about what that means. If the reaction moves from entirely reactants over to entirely products, you'll have a number up on the top that's big and a number on the bottom that's very, very, very small because there's almost no A or B left. That means the equilibrium constant will be very, very large. So if the reaction moves, again, strongly from left to right, the number for Kc will be very large. If the reaction barely moves at all from left to right, let's say you start off with all reactants A and B, and only a little bit of those reactants turn into products C and D, so that you still have a lot of A and B left and very little C and D, then the Kc will be very, very small. It will be a positive number. Equilibrium constants are always a positive number, but the numerator on top, C and D, will be very small compared to the denominator on bottom, so the equilibrium constant will be very small if very little of the reactants A and B turn into products C and D. The exponent on the concentration of each substance is the coefficient of that substance in the chemical reaction. Generally, the equilibrium constant indicates how far the reaction has moved from reactants to products. So there's the same law of mass action. If the products are much greater than the reactants, Kc will be large. So large Kc when there's a large fraction of products over a very small fraction of reactants. If the reactants are much greater than the products, in other words, either the reaction has moved back towards reactants to the left, or very little of the reactants turn into products, then Kc will be small. So small Kc when there's a small fraction of products and a very large fraction of reactants. So we're going to actually use some numbers. So a sample of hydrogen and iodine are mixed in a 1 liter vessel at a temperature of 430 degrees centigrade. Once equilibrium is reached, it is determined that 2.5 moles of HI, hydrogen iodide, 0.25 moles of H2, and 0.5 moles of I2 are present. What is the equilibrium constant Kc of the reaction at this temperature? So the first thing I want to point out in this reaction, you're dealing with molar concentrations. The second thing is they give you a temperature of 430 degrees. The equilibrium constant Kc is a function in part of the temperature. So if that temperature were different, the value of Kc and therefore the concentrations would be different. So you really don't need to use the 430 in the problem. What they're really saying is that the temperature is going to remain the same. That's the key, because if the temperature changes, the equilibrium constant changes. So there's the reaction. It's a simple synthesis reaction. H2 plus I2 gives you 2HI. It's balanced. So that would be the law of mass action. You take the HI, the product, you put it on top. The coefficient of HI is 2, so that becomes an exponent. Then the reactants over on the left side, H2 and I2, go on the bottom. They have coefficients of 1, so you don't have to write those. And so that would be the law of mass action for this particular reaction. Now you can plug in the equilibrium concentrations. So Kc indicates we are dealing with an equilibrium concentration of molar concentration. And there's several different types of equilibrium constants. We need molar concentrations for each equation. Since the reaction takes place in a 1 liter vessel, the moles also represent molarity. So 0.25 moles over 1 liter is 0.25 molar, for example. 0.5 moles over 1 liter is 0.5 molar, capital M. And the 2.5 moles of HI is 2.5 molar. So there we go. So we're going to substitute the values. So the product concentration 2.5 squared over 0.25 over 0.5. And when you do the math on that, you get 50. So that has an equilibrium constant of 50. This means that a numerator containing the products is about 50 times greater than the denominator containing the reactants. Actually, that's not exactly true because you're squaring the numerator and there's some other things going on there, but that generally means that the products are much greater than the reactants. Okay, so let's write some laws of mass action for this, okay? So there you have lead chloride. This is a solubility product reaction because lead chloride, generally speaking, does not dissolve. It's insoluble, but a tiny amount will. And what the K value over there, it should really technically be KSP, will tell you what that solubility product is. Anyway, here's some rules as we go along. So we put the the products on top, Pb2 and Pb2 plus and the 2Cl. So that gives you the law of mass action you see on the right. Now what happened to the solid over on the left? Shouldn't it be on the bottom of that equation? Well, if it's a solid or a pure liquid, you do not include it in the law of mass action. Okay, so again, if it's a solid, which it is in this case with an S, or a liquid with an L, you do not include it in the law of mass action. Only concentrations that are aqueous. So PbCl2S does not appear in the law of mass action equation because it is a solid. Here's another example. You have hydrochloric acid, you're putting it into water, which is a pure liquid. You produce what are called hydronium ions. We're going to learn about that when we get to acid bases, and chloride ions, okay? So if you look at the law of mass action over there on the right, you have the products, which is hydronium, H3O plus, and chloride, which is Cl minus, and they're in concentration form. That minus sign should be inside the bracket. And then on the bottom, you have HCl, which is in solution, that's hydrochloric acid, but you don't include the water because it is a pure liquid. So H2O does not appear in the law of mass action equation because it is a liquid. So equilibrium constants do not have units. Examples, write the equilibrium constants for the following reactions. So how about that? Go ahead and do that. Pause the video. I'm going to continue on, but you pause the video. Try to do that, or at least do it in your head. And this is what you get. You get the equilibrium constant is the product over on the right. That goes on top. You use the coefficient as the exponent. The reactants on the left, 2NO, that becomes NO squared, concentration of NO squared. And the chlorine molecule is Cl2. Try this one. Again, don't let the charges fool you. Those have nothing to do with the equilibrium law of mass action. They're simply the charges on those particular ions. So you notice everything there is aqueous. That means everything is going to go into the law of mass action. So there it is. Read that and be sure you understand why it's written that way. The only one that has an exponent is the bromine, which has a coefficient of 4, so that becomes an exponent. How about this one? Again, this is a solubility product because silver chloride, from your solubility rules, we say is insoluble. However, tiny amounts do dissolve, and so we need to know what those tiny amounts are, and that's silver chloride decomposing. And so there you go. Convince yourself that that's correct. The AgCl does not go in the law of mass action because it is a solid. Otherwise, it would go down on the denominator on the bottom of that fraction. Okay, and there's the one we saw before. So we have HCl, water, which is a liquid, and then you have hydronium, H3O plus, and chloride. And there you go. It's the same one we saw before. Okay, and that takes care of this introductory lecture of equilibrium constants and equilibrium in general. And we'll pick this up in the next lesson.